Hello everyone, my name is Joseph and I'll be talking about edge weight predictions in weighted sign networks. Here is what we'll be covering in the presentation. So weighted sign networks are networks in which edges are labeled with positive and negative weights to capture likes or dislikes, trust or distrust, and other social relationships between people. The aim of this paper is to predict the weight of edges in real-world weighted signed networks for the very first time. This will be done by taking 6 real-world WSNs as inputs to predict the weight of their edges. Here's the methodology used by the authors of this paper. They defined two novel metrics, which are fairness and goodness. So fairness is referred to the measure of how fair a vertex or user is in assessing other vertices or users. And while goodness is the measure of how good a particular vertex or user is perceived by other vertices or users. And then they define two axioms. One is the fairness axiom, and the other is a goodness axiom. The fairness axiom states that a vertex is fairer than another if it gives ratings closer to the ratings deserved by the recipient, while the goodness axiom states that vertices with higher fairness have higher impact on the vertices they rate. So this actually tells us that the fairness and the goodness metrics, they are interwoven. One relates to another. And then there's a fairness goodness algorithm, and the algorithm needs to satisfy these four properties, and then we'll test for experiments. So let's go deeper into this paper. Here's the fairness and goodness algorithm, which will be explained in later slides. But it's good for us to note that the interval of the fairness scores lie between 0 and 1, while that of the goodness scores is between -1 and 1, while that of the edge weights is also between -1 and 1. How good is the fairness goodness algorithm? Let's take a look at that from this example. Given this weighted sign network we have here and the fairness and goodness algorithm, we have an input of a WSN, weighted sign network, that has these values V, E, and W. V represents the set of vertices or users in the network, which is from this case node A to node G, and E represents the edges. The blue edges here represent the positive edges, while the red one represents the negative edges. And W represents the weights of all the edges. And this is to give an output for all the fairness and goodness scores for all the vertices. And now we have some predefinitions here. F represents fairness, J represents goodness. This simply means that for all of these nodes, they have a default fairness and goodness value of 1. And now we have a counter t is equal to -1, and we come to this loop. Yeah, so that means t is going to be 0. And this formula represents the formula for goodness and this formula for fairness. So let's assume that there's a relationship between a user u and v, and let's assume u is this node A and v is node B. So in this case, we're going to calculate, since t is 0, so we have g of 1. That means the first iteration for the goodness value of b is equal to 1 over the in links of b. How many in links does b have? It has 4 in links: 0.5, 0.7, -1, and 0.7. So we have 1 over 4. Then the summation of all the in links is going to be f of 0 of u is 1. So 1 multiplied by 0.5 plus 1 multiplied by 0.7 plus 1 multiplied by -1 plus 0.1 multiplied by 0.7. That will give us, once we solve that, that will give us the goodness value of b. Then we come to the fairness value of u, which is a in this case. So the formula tells us to find the outlinks of A. How many outlinks does A have? It has two outlinks, that is 0.5 and 1. So we're going to have 1 over 2 into absolute value of 2, since it has two outlinks. Then summation of all the outlinks that A has. In this case, um, the first one is A to B. So weight of A to B is 0.5. 0.5 minus the goodness value of B, which is B in this case. And so we're going to input the value here. Then plus the next weight, A to C, that is 1 minus the goodness value of C. So we should have gotten the goodness value of C normally. So we put the goodness value of C and we get the fairness value. So this formula actually continues as long as the present fairness value less the previous fairness value is greater than an error bound, this small e, which is set to 0.001, or when the present goodness value less the previous goodness value is greater than this error bound. So once this condition stops being satisfied, then the algorithm is set to have reached convergence. Then it returns the final value, the final iteration value, as the values for the fairness and the goodness. Here are the remaining results of the example we just did. From the iteration number, we can see that the algorithm converged at the 8th iteration for this example. And here are the other scores. So let's move on. Though this paper about predicting the weights of edges in weighted sign networks is the first of its kind, the authors compared their work to others done in signed social networks, compared it to algorithms used for edge sign prediction in social sign networks and those used for edge weight prediction in unsigned social networks. They used 11 algorithms, which include reciprocal, tidal trust, bias and deserve, and PageRank on this 6 real-world data sets, which include Bitcoin OTC, Bitcoin Alpha, and Twitter. Next, we'll be looking at these experiments and their results. And it is good to note that the root mean square error and the Pearson correlation coefficient were used to compare the results of the algorithms that were used in this experiment. And a low root mean square error and a high Pearson correlation coefficient is regarded as the appropriate score for an algorithm to be considered as being accurate and precise. This experiment one uses an unsupervised learning approach, and it is such that for this network, for example, an edge is removed and the remaining part of the network is fed as an input to all these algorithms. The algorithms then try to predict the edge weights of the missing edge, and this is done for each edge that is removed randomly, and then the scores are average, and here are the average scores. And we can see that the fairness goodness algorithm actually performed best across the 6 data sets. So let's move to the next experiment. Next is experiment 2. This used a supervised learning approach. Here, a first edge is removed from the network, then a second edge is also removed. And afterwards, the algorithms that were earlier used um, in the previous experiments were used to run the network with the missing edges multiple times so as to train the model and generate a feature from the edge weight prediction of the algorithms and a label which is actually the edge weight of the second removed edge. And the learned model was thereafter used to predict the edge weights of the first removed edge. So it was noted that the supervised learning produced better results for all the algorithms than that of the unsupervised learning um, approach, which was used in experiment one. And but however, the fairness goodness algorithm with linear regression had the best result across the six data sets. This further implies that the trained model can also be used for other real world scenarios and will also yield accurate results. So let's go on to the next one. Here is experiment three. Here, a certain percentage of the edges are removed, specifically from 10% to 90% in steps of 10%, as seen in the graph here, just to observe the effect of removing the missing edges. And after the removal of the edges, the algorithms are used to run this network and predict the edge weights of these missing edges. And from the graph here, we can see this is the results for Bitcoin OTC. We can see that the root mean square has the least value and the PCC has the highest value, which is actually the recommended value. PCC is meant to be higher, while root mean square is meant to be least for the algorithm to be considered as accurate. So in this case, the fairness goodness algorithm is quite robust and accurate, as seen in this graph. For the other data sets, we can see that it's the same across board. I will explain this gray line later in the next in the next experiment, but we can see from this that the root mean square across the other five data sets were the least, and the PCC value across the remaining five data sets was the highest for the first four data sets, and here it was the third. Experiment 4 is similar to what was done in experiment 2 in that they both used supervised learning approach. In this experiment 4, a certain percentage of the edges are removed, in this case from 10% to 90% in steps of 10, and these are fed into the algorithm, which are used to train the model. And then after the model has been trained, the model is then used to predict the edge to predict the edge weights of the missing edges. And just like experiment 2, the values for all the algorithms were significantly better than that gotten from the unsupervised approach as done in experiment 3. And we can see from the graphs here, this gray line represents the linear regression model using the fairness and goodness algorithm. And we can see the root mean square has the least values basically across all of this data sets. And for the PCC, you can see that it has the highest values across all these data sets. So this affirms that the fairness goodness algorithm is scalable, is robust, is quite effective, and that you can actually take this model and use it for other real world scenarios and to also give us accurate results. To conclude, this paper shows us that the fairness and goodness algorithm can be used to predict edge weights in weighted sign networks with higher precision than other well-known algorithms. The algorithm is also seen to be robust to network sparsity and also able to converge to a unique value. Thank you very much for listening to the presentation.